Jai Hind students. So today we are going to start another topic, that is the clamper circuit. This is another application of the diode. So what are the clamper circuits? Clamper is a circuit which will add a DC level to the existing AC input signal. Actually what happened, the positive peak or the negative peak of the signal that can be placed with the help of the clamper circuit at the desired level. So actually it shifts the DC level to the another level. So because in case of clamper circuit, DC level gets shifted, that is why the another name of the clamper circuit is level shifter. Basically any clamper circuit, it consists of an additional component which is in addition to the two components, that is the diode and the resistor, which we use in the clamper circuit. Here we use one more component, that is the energy storage element, and which is nothing but the capacitor. So a clamper network consisting of three basic components. One is the diode, second is resistance or resistor, and the third one is the capacitor. And it shifts the DC level, the clamper circuit, it shifts the DC level to the another desired level without changing the appearance of the input signal. That means the signal peak to peak value, peak to peak input voltage of the input signal will remain same, whereas the shape of the signal also remains same. The only thing is the DC level gets shifted. So how do we? Yeah. So basically clamper circuits are divided into two categories, that is the positive clamper and the negative clamper. So here you can see in this circuit, in this case, the case 1, the DC level has been shifted downward, whereas the peak of the signal has been shifted upward. So that is why it is called as the positive clipper. Whereas in case of the negative clipper, you can see that the signal peak has been shifted downward, and that is the reason it is termed as the negative clamper. So clampers are again divided into two categories. It can be the biased clamper or it can be the unbiased clamper. So if there is only three components are connected as shown in the figure, that is the capacitor, diode and a resistance, then it is unbiased clipper. So when we start our analysis, so we have to start the analysis by examining the response of the portion of the input signal that will forward bias. Actually, we in case of the clamper circuit, this is very important to note that we start our analysis when and only when our diode comes forward bias for the first time. That means if the first positive, during the first positive half cycle, if your diode does not come in the forward bias state, we cannot start our analysis. What is the reason behind this? See, there is a tau is the charging time constant which is required for charging or discharging of the capacitor. So whenever your capacitor, and this tau is very high value, that is around, that is nearly 5t. That means it requires 5 fundamental time period of the input signals are completed during this charging or the discharging of the capacitor. So we always prefer that the capacitor should be charged through this diode, and that will be only possible when your diode will be in the forward bias state. And as soon as your diode will come for the first time during the for the first time it will come in the forward bias state, then it will offer you zero resistance. That means it will act as short circuit, and if it will act as short circuit, that means it will offer you zero resistance. As we know that the ideal diode give the resistance during the forward bias condition, it will give the, it will offer the 0 resistance. So, as also we know that current will always follow the least resistance path. That means that the current, when the diode is in a forward bias state, then current will be following this loop. It will not be following the second loop, that is the no current will pass through this resistance, because the value of the resistance is very high in comparison to the diode forward resistance, which is of the order, ideally it is 0, whereas in it is practically even it is, the value is very few tens of ohms. So, because this resistance value is very less, that is why the charging of the capacitance will be very fast. But if your diode is in a reverse bias state, that means then in that case it will be open circuit, and if your diode is in open circuit mode, then the capacitor will try to charge through this resistance, and which will require the time which is equal to 5t, and so that it will never. So, what happened? The capacitor will try to charge to the peak value, but it will not be able to, because it will take 5t, 5 time period of the cycle of the input signal. That means it will charge and discharge, again charge and discharge. That means it will never be able to charge to the maximum value. So, that is the reason we always start analysis when and only whenever diode comes in the forward bias state. So, there are few important points regarding whenever we are dealing with the clamper circuit. The first point, that it shifts the DC level. Second, it consists of the 3 components, that is a diode, resistance and a capacitor. Peak to peak value of the input signal remains same after passing through the clamper circuit. The shape remains same. And the fifth and the foremost important point is, we start our analysis when and only when our diode comes in the forward bias state for the first time. So, these, whenever you are solving any clamper circuit, so always keep these 5 points in your brain or in your mind, then only you will be able to handle these circuits very accurately. Okay. So, let us start analyzing the circuit, the unbiased circuit. Here, during the first positive half cycle, let us see that the signal which we are applying is a rectangular waveform. This is your input signal, and this is time period. Here it is 0, this is t by 2, this is t. So, during the time period 0 to t by 2, our terminal A and this is terminal B. So, terminal A will be at positive potential and B will be at negative potential. So, this positive and negative will make your diode forward bias, and it will be, so diode is forward bias means we can start our analysis. Initially, we assume that all the capacitors are in a completely discharge mode. So, as soon as your diode is in a forward bias state and it will offer 0 resistance, so it will be replaced by a short and the current will be following the path like this. So, if your current is following like this, that means this will be at positive and this will be at negative potential. This plate of the capacitor will be at positive potential and this plate will be at the negative potential, because we know that the current will always flow from higher potential to lower potential. Also, so if I write the KVL in the first loop, then what will be my KVL? It is VI minus VC is equal to 0, and let us say this VI is maximum value, that is Vm. So, what will be your value of Vc? It will be, VI will be equal to Vm. and because this value comes out positive, that means we will retain the sign which we have taken. Also, in the second loop, what will be the output voltage? V0 will be equal to how much? If I look at this, so across this, because resistance is 0 and if current is passing through this diode, whatever current is passing through this diode, because resistance is 0, so the voltage across this diode will be 0 and in parallel voltage is same, so V0 will be equal to 0. So, in the first half cycle, what we have find out that first is that capacitor has been charged to the value, let us say this is Vc and that has been charged up to the value Vm, and in the second thing that output voltage is equal to 0. So, this completes our first half cycle. Now, coming to the second half cycle. Now, during the second half cycle, this terminal will be at negative potential and this will be at positive potential. Also, our capacitor is charged to the value Vm with this polarity marked plus and minus. And the diode position was something like this. I am drawing here just to show you. So, diode is like this, and here we can see this negative and this negative. These two will get added up and this will make your diode, this diode, reverse bias. So, if this diode is reverse bias, it will offer you infinite resistance, that means open circuit. When it will be open circuit, then your loop will be this. So, now we will write the KVL in the outer loop. So, if I write KVL, it will be minus V M, because it is a rectangular waveform. So, whenever we apply the input signal, it will be the maximum value, that is Vm, that is why I am writing here Vm, minus Vm minus of Vc minus V0 is equal to 0, and Vc is Vm we have calculated in the first half cycle. This is the second half cycle, that is T by 2 to T time period. So, keeping the value of Vm here, Vc here, that is Vm. So, we get V0 is equal to minus of 2 Vm. So, if I draw the output waveform, this is V0, this is T, this is T by 2 and this is T. So, 0 to T by 2, what is my output voltage? It was 0 volt. It was 0 volt, and T by 2 to 2, it is minus of 2. So, here you see the DC level, initially the DC level was at this position and it is shifted upward, right, but the peak has been shifted towards the down, that means it is a negative clipper. Also, this is very interesting to notice that the value, the amount by which this DC level has been shifted, that is equal to Vc. If your Vc is positive, then it will be shifted upward, and if the Vc is negative, then this DC level will go down. So, this is very important to see that what is the value. So, here you can see that the peak to peak value remains, this is what? This is 2 Vm. So, this value is 2 Vm. So, here you can see the peak to peak value was Vm, and this was also Vm. So, peak to peak value remain same, because this is also 2 Vm and here also we are getting the 2 Vm. Second thing, that the DC level has been shifted upward by an amount of the Vc, that is the capacitor voltage, and the shape remains same. Initially we are having the rectangular waveform, in here also we are having the same waveform, that is the rectangular waveform. So, this is the most simplest circuit of the clipper, that is the unbiased negative clipper circuit. So, this we have already discussed. Okay, fine. Now, coming to the second circuit, in this circuit we can see that the diode orientation has been changed from the previous circuit. Also, an additional battery has been connected in the circuit. So, again we will start our analysis from the first half cycle, and always remember that whenever we are doing analysis, we must complete the analysis for at least one complete cycle. That means, if at all during the first half cycle your diode is in a reverse bias state, then we have to move on to the next one complete cycle, because in the first half cycle we were not able to do the analysis. What actually we mean, that we'll understand in a better way when we will be solving this problem. So, let us start. Here in this figure you can see that during 0 to T1. So, let us mark these two terminal as, let us name them A and B. So, during the 0 to T1, during the time period 0 to T1, terminal A will be at positive potential and B at negative potential. So, this will make your diode forward bias or a reverse bias. Anyone a student can answer? It will be reverse bias. Reason, although this 5 volt will try to make your diode forward bias, but here you are applying a rectangular waveform, and which is 10 volts. 10 volt is greater than this 5 volt, and this 10 volt is making diode reverse bias, because here the cathode is connected through this capacitor to the positive terminal of the battery. So, that is why in the first half cycle, that is 0 to T1, diode will be in a reverse bias, and we cannot start our analysis for the first half cycle until and unless our diode comes in the forward bias state for the first time. So, here you can see that for the first half cycle, that is 0 to T1, your diode is in a reverse bias state. That means our capacitor will not get charged, so that we cannot start our analysis. So, what we can do? We can say no analysis. If we are saying no analysis, that does not mean that output will be equal to 0. We are only saying that during this time period, we are not able to do any analysis, and we are not able in the position to tell that what will be the voltage at the output during that time period. We will be able to tell this only after completing one cycle. That means one cycle, another half cycle will be T1 to T2 and T2 to T3. So, after we will analyze this T2 to T3 time period, we can tell that what will be the value during the time period 0 to T1, because this is a periodic signal. So, whatever value we are going to get here, the same will be the value in the previous half cycle. Okay. So, let us move on. So, first half cycle 0 to T1, the diode is in a reverse bias state, and whenever your diode comes in the reverse bias state for the first time, means diode is not coming forward bias, then we say no analysis. We can start our analysis when and only when our diode will come in the forward bias state for the first time. So, that is very important point to be noted while you are dealing with the clamper circuit, because if you will not follow that rule, you will end up in a problem and you will never get the right result. Okay. So, coming to the next half cycle, that is T1 to T2. Now, during T1 to T2, the terminal, because we are entering in the negative half cycle, so terminal A will be at negative potential and B will be at positive potential. So, now this negative will try to make your diode forward bias, because now you are applying a value 20 volts, which is negative voltage. So, that negative together with this positive 5 both voltages together will try to make your diode forward biased. So, for that reason your diode will be, and here you are considering the diode as an ideal diode. So, diode will be forward bias. So, if it is forward bias, that means it will be short circuit, and whenever it is short circuit, so your current will follow this path. So, remember, we will always take the direction of the current clockwise. Initially, we always assume that diode, the current is flowing in the clockwise direction. So, if my current is flowing here in the clockwise direction, so the potential that will be developed across this capacitor will be plus and minus, because current flows from higher potential to lower potential. So, that is the reason we will now write the KVL for the T1 to T2 time period. So, in the first loop, let us say this is the loop 1 and let us say this is your loop 2. So, in the first loop we write the KVL, so that it is minus of Vi minus Vc minus 5 volt is equal to 0. Vi is equal to 20 volts. Now, it is minus 20. This is very important to note, because we have already taken care of the sign in the KVL itself. So, you need not to write again here minus of 20. If you write minus of 20, then it will become plus, because this minus and this minus of this value, this will make your net voltage positive. So, remember, we always consider the sign in the KVL itself, and after that we will put only the magnitude, not the value along with the sign. ऐसा करेंगे then it will be a wrong problem. Okay. So, minus 20 minus Vc minus 5 is equal to 0. So, Vc comes out to be, Vc is equal to minus of 25 volt. So, this minus 25 volt, what does it signify? It signifies the first thing, that whatever sign we have taken the sign of the opposite polarity. That means we have to change the sign. If this minus, if the minus is coming in the equation, that means we should have to change the polarity here. So, that is the reason we have to change the polarity. Instead of this, actually we have to take this polarity. So, my capacitor has been charged with this polarity and the value 25 volts. So, this is the one thing. Next is, what will be the output voltage when your diode is the forward bias state. So, we will write the KVL in the second loop. So, this is plus, this is minus V naught, this is plus and minus 5. So, if I will write KVL, so minus of 5 minus V naught is equal to, sorry, plus 5 minus V naught is equal to 0. So, V naught comes out to be 5 volt. Okay. So, we have got two values. One is the capacitor is charged to the value of 25 volt with the polarity marked with red color, and because this minus sign has been coming, and second is output voltage will be equal to 5 volts. So, this is only during the time period T1 to T2. Now, because in the time period 0 to T1 we were not able to do any analysis because the diode was in a reverse bias state. That is the reason we have to, in order to complete one cycle analysis, we have to do the analysis for T2 to T3 also. So, okay. So, now during time period T2 to T3, again your terminal A will be at positive potential now, because now we are in the positive half cycle, and terminal B will be at negative potential. So, in this case, now we have to concentrate on this sign on this sign. So, we can see this plus and this plus will make the diode reverse bias. So, it will be open circuit, and if it is open circuit, then your KVL will be, your equivalent circuit would be, this is open and this is RL. Here we are measuring the voltage V naught. This is plus and minus Vi. This is minus and plus Vc, and this is plus and minus. So, this is the equivalent circuit. Now, we have to write the KVL again using the current direction. Again, in order to simplify the problem, I always take the direction of the current in the clockwise direction, so that whenever if the sign is negative in the out voltage, then we can say that we should have taken this current in the opposite direction. So, we just change the polarity. So, basically you need not to worry about the direction of the current. You can always take the direction of the current in the circuit as a clockwise direction, and automatically if you are taking the direction opposite, then automatically negative sign will come in your equation. So, we need not to worry about that. So, that if I write the KVL here during T2 to T3 using this equivalent circuit, so it will be V input plus Vc minus V naught is equal to 0. Vc is equal to 25 volt. Again I am repeating that now I will not write here minus 25, because I have already taken care of this sign by changing the polarity here. So, that is the reason I will keep only the value here. So, Vi is during the T2 to T3 10 volts plus 25, and that is equal to V naught. So, V naught is equal to how much? 35 volts. So, if I try to draw the circuit output voltage here in this case, so how would I draw it? It will be 0 to T1, I will write no analysis. You need not to draw anything, just write no analysis. Now, T2 to T3, the value is plus 5 volt, here you can see. So, I will mark here plus 5. Now, T2 to T3, it is plus 35. So, I have to draw this plus 35. So, see, this is 5 volt, this is 5 volt, this is 35 volt. Initially, you were in the position, if this is so, the net voltage here to here it will be 30 volts only, and this was your original signal. This was 20 volt and this was 10 volt. So, see how much we have shifted our DC level, minus of, if this is 35 volts, so how much we have shifted our DC level? It is 20 and 5, so 25 volt, and it is shifted downward because Vc is minus of 25 volt. So, if you look at in this circuit, so you can say that from here it has been shifted to the value, this is only 20 and 25. So, this is your output voltage. So, here you can see that the shifting has been taken place towards the downwards direction, because the voltage comes out to be minus 25. If it is plus 25, then the DC level would be shifted upward. Any question? Yes, Pratyaksh Shrivastava, would you like to ask anything? It will be nice if you will keep on asking the question, then it is much easier for us to explain the things. So, you should take the advantage of these online sessions. You may ask any question, any doubt. Okay, fine. So, I'll move on to the next problem. Okay. So, this is the another circuit which I would like to take up. Here the diode is connected in a fashion that during the first positive half cycle your diode is going to be in a forward bias state, that we can see with the help of the direction of the diode. Okay. So, during the time period 0 to okay, fine, I should draw it again here. This is my input signal Vi, and this value is taken as 12 volt and this is minus 12 volt. Let me mark this as 0, T1 and T2. So, during the time period 0 to T1, what will be the condition of diode? The diode will be in a forward bias state, but it is important to notice now that diode is taken as the silicon diode. This is a very commonly made mistake during the exam, that sometimes the students, they don't bother about, or they don't they just they just, you can say that they are just careless enough, so they didn't realize that whether this diode is a silicon diode or it is a germanium diode or it is a ideal diode. So, this is very important that we must be very careful while dealing with this, that whether the diode is an ideal diode or it is a some practical diode, silicon or germanium. So, in our case it is the silicon diode. So, diode will be in a forward bias state during the first positive half cycle, and because we are applying the directly how much voltage, 12 volts. So, this terminal will be at positive potential and this terminal at negative potential. So, this will make your diode forward bias. So, as soon as your diode forward bias, the equivalent circuit would be so, this silicon diode will be replaced by a battery of 0.7 volt. Why 0.7? Because this is the barrier potential of the silicon material and this is the amount of the voltage which is required to turn on this diode. So, that is why this much amount must be applied to this diode in order to make this diode on. So, that is why this will be replaced by a voltage of 0.7 and minus plus, this is 2 volts, here we are having the resistance, whatever value it is, plus and minus, and this is we know. So, this is your equivalent circuit. Now, if I see, because the forward resistance of the diode is very small in comparison to 56 kilo ohm, this is only some few tens of ohm, let us say 75 ohms or something. So, 75 ohms is a very small value in comparison to that 56 kilo ohm. So, the current will not follow this path because this is a very high resistance and the current will always follow the low resistance path. So, that is why the current will be moving through this loop. Here you are having plus and minus and Vi. So, if I write the KVL here for this circuit, the first loop, then what will be? My equation, it is Vi. So, let us mark because current direction is this. So, this is Vc this is plus and minus because current flows from higher potential to lower potential. So, Vi minus Vc plus minus minus and plus. So, minus 0.7 plus 2 volts is equal to 0. And Vi is 12 volt. So, keeping this value here, 12 plus 2 minus 0.7 and this is equal to Vc. So, Vc comes out how much? 13.3 volts. So, this is your Vc. Also, in the second loop, this is your second loop. So, in order to calculate the output voltage during the time period 0 to T1, we have to write the KVL for the second loop as well. So, if you write the KVL, I am writing here. So, this is minus 2 plus 0.7 minus V naught is equal to 0. Let us check if it is correct. Minus 2 plus 0.7 minus V naught is equal to 0. So, V naught comes out to be how much it is? V naught is equal to minus of 1.3 volt. And Vc is. So, because here in this case Vc is plus 13.3 volts, so you will retain this sign. So, this is plus and this is minus Vc and the value is 13.3 volts. And let us say this is V naught 1, the voltage during the time period 0 to T1, it is 1.3 volts. Now, coming to the next half cycle, that is T1 to T2. So, it is minus and this terminal will be at positive potential. So, now this minus and this minus both are the negative sign. So, this will make your diode reverse biased or forward biased? Anyone? Reverse biased, because this is these both are the negative sign. So, the diode will be in a reverse bias position, and if it is in a reverse bias position and if you will draw the equivalent circuit. So, what you will, how will you draw it? It is minus plus Vi plus minus Vc. This will be open circuit, diode will be open circuit, and here you are having V naught plus and minus. So, now again write down the KVL for this loop. So, if I write the KVL, so minus Vi for this loop minus Vc minus V naught is equal to 0. So, how much Vi? 12 volt again, because we have taken care of the sign or of these signals itself in the KVL. That is why we will not again put the sign here, we will write only the magnitude. So, that is why this is minus 12 and minus 13.3 volts, and that is equal to V naught. So, V naught is equal to, or V naught 2 is equal to minus 25.3 volts. Okay. So, now let us see. I am drawing your original signal with the actual DC voltage. This was your actual DC voltage and this was your signal. Now, I will show you how we are drawing. So, 0 to T1, what is the output voltage? It is minus of 1.3. So, it is actually minus of 1.3 volts, and V naught 2 is minus of 25.3. So, this is 25.3. So if this is 21.3 and this is 25.3, then how much this will be? 24 volt. And how much DC level has been shifted here in this case? You can see it is plus 13.3 volts. It has been shifted 13.3 volts. See, the center of this 24, this is 12 volt, this is 1.3. So the net voltage, that is how much? It is 13.3 volts, and it is shifted upward. You can see that this DC level has been shifted upward. So now this is my original signal, and my DC level has been shifted by 13.3 volt, and because this is a positive voltage, because this is a positive voltage, that is why the DC level has been shifted upward. This is the another problem. Suppose you get, instead of, up till now we have solved the problems which are having the square wave. What if you are having a signal which is a sinusoidal wave? Because in case of rectangular waveform, we apply the voltage and you will get the output. Means you directly forward bias your diode or reverse bias, because that will give you the maximum voltage in the at time t is equal to 0 only itself. Whereas here the value is continuously gradually changing. So under such type of problems, the simplest way of solving such type of problem is, you first of all enclose this signal into the envelope, and now treat this value, solve this problem. So if I solve this problem, so 0 to T1 and T2. So during time period 0 to T1, your diode will be in a reverse bias condition. Let me take this value as 20. Let me take this value as 20 volt minus 20 volt. Let us take this value as 5 volt. Okay. So during 0 to T1, diode is in a reverse bias condition. So 0 to T1, diode will be reverse bias. So no analysis. Now T1 to T2 time period, this is minus, this is plus, this will make your diode forward bias. So if diode is forward bias, current direction is this. So this is plus and minus Vc. So if I write the KVL, so it is minus of Vi minus Vc plus 5 is equal to 0. So here in this case, Vi is how much? 20 volts. So if I'll keep the value here, Vi is 20 volt, then Vc will be equal to how much? It is minus of 15 volt. So if it is minus of 15 volt, and also in the second loop, if I write the KVL for this loop, then V0 will be equal to how much? It is minus of 5 volt. So this is the during time period T1 to T2. Now during time period T2 to T3, this will be plus and this is minus, and capacitor has been charged minus of 15. That's why you have to change the sign, and this value is 15 volts. So this plus and this plus will make this diode reverse bias during the time period T2 to T3, diode is in a reverse bias condition, and if diode is in reverse bias condition, it will be open, and if it will be open, then you will write the KVL in the outer loop. So it is Vi plus Vc, because now we will take the sign, this sign. So Vi plus Vc minus V naught is equal to 0. So that is equal to V naught, and Vi is how much? Plus 20. Vc is how much? 15. So V naught will be equal to how much? 35 volt. So if I draw during the time period 0 to T1, no analysis. Now during the time period, now first of all, for the such type of sinusoidal signal, what this is very simplified way of drawing it. First of all, you draw the original signal. So this was your original signal, and you just need to shift the DC level by an amount of this Vc. So because this here the Vc is given as minus of 15 volts. So what is required? You just draw this DC level, shift this DC level. This is 20, this is also 20, and we have to shift the value by an amount of minus 15 means you have to, minus means you have to shift the DC level downward, and how much value? 15. So I'll draw a line here. This is your actual line. So this will be my signal. So let us see if it is correct. During the time period 0 to T1, what is my output voltage? It is minus 5 volt. So here you can see this is 0 to T1 and T1 to T2. So it is the duration when we are in the T1 to T2, because in this time period there is no analysis. So that is the no analysis time period, and T1 to T2, this value comes out to be minus of 5 volt. Here you can see this is, if this is 20 and this is 15, then this must be 5 volt only. And in the time period T2 to T3, what is the value? It is plus 35. So here you can see this is 20 and this is 15. So net value is plus 35. So here you can see. So under such type of situations, if you get any signal, sinusoidal type of signal, so there are the two steps you have to keep in mind. First of all, enclose the sinusoidal signal into the enclose this so that that sinusoidal voltage signal will be converted into the square wave. Calculate the values and just draw the original signal and shift the DC level by an amount of the capacitor voltage. If it is positive, then shift that DC level upward, and if it is a negative voltage, then shift that DC level downward. So this completes the clamper circuit. I hope this this will be fruitful for you, and for any queries you can always join my classes, and you can ask your questions. So thank you so much everyone. Take care. Jai Hind.